Hello everybody. I was the principal scientist at the International Rice Research Institute for 25 years. Now I'm a visiting professor at the Chang University. I'm glad to be able to speak to you about agroecological technology and how it is so important to enhance farmers' literacy by designing innovative messages. Our traditional approach towards helping farmers has been to train farmers to recognize pests and natural enemies and spray when necessary, assuming that farmers understand the ecological principles behind the recommendations. However, in a recent paper we published, we found that ecological illiteracy is rampant, and this in fact deepens farmers' pesticide dependency. That is why farmers do not favor environmental practices because of ecological illiteracy. Farmers' training programs focus on improving farmers' knowledge and skills. However, they may not necessarily translate into improving farmers' decision-making and practices. And in many cases, despite changes in farmers' practices, these do not sustain, and very quickly farmers revert back to using pesticides as before. Most farmers could recognize spiders, but they do not know and understand biological control. In the 1980s, insecticide use of farmers in Indonesia declined drastically. This is in part due to the government's removal of pesticide subsidy from 85% subsidy to zero subsidy. And in its place, the government introduced IPM training, and as this chart shows the increase in IPM training as into the 1990s. And although there were IPM training increase, insecticide use has also increased. Throughout the 1990s in Indonesia, insecticide use had been relatively low. However, from the late 1990s onwards, there was a drastic increase of insecticides, about 5,895% increase. Today, it is very common to find farmers in Indonesia spraying insecticides 8 to 12 times, which is the highest in the region. This chart clearly shows that the training program had not been sustained. Most of the training program had lacked ecological content. Training programs usually do not include key ecological principles. Farmers therefore lacked the confidence in sustaining the changes they had made initially. Ecological principles such as predation, parasitism, plant compensation, secondary pest development, naturally occurring biological control mechanisms, and the impact of insecticides are not clearly taught. Ecological processes are not easily observable and thus often have delayed effects, and thus it is difficult to teach such principles. It's easier to teach farmers to recognize spiders, but not so easy to teach farmers predation. In addition, pesticide marketing in Southeast Asia is poorly regulated and thus allowing pesticides to be sold as fast-moving consumer goods or FMCGs with aggressive advertising, fake information to create fear, sales, and a lot of incentives and marketing campaigns to entice farmers to spray unnecessarily. Thus, it is important for us to develop new training innovations so as to empower farmers. We need to transform ecological principles into simple rules or heuristics so that it is easily understandable. Use the principles of psychology to create games, analogies, and farmer experiments to enhance learning using experiential learning methods, and to communicate these rules and games through mass media such as multimedia campaigns, entertainment education programs on radio and television so as to upscale and reach the millions of farmers. In this presentation, I will share with you a few examples of these innovative methods of training. First, using cognitive dissonance technique. Many farmers in Asia spray their crops early in the season thinking that these sprays will protect their fields from insects, especially leaf feeders. Ecological research we've done for many years showed that these sprays are unnecessary, wasteful, and even more damaging to the production. At early crop stages, a huge diversity of predators would invade or migrate into the rice crop from neighboring habitats. Spraying at this time would just be counterproductive, as they will destroy millions of naturally occurring biological control agents. Because of plant compensation abilities of the rice crop, these damages at the early crop stages have no real consequences. These ecological concepts were distilled into a simple rule. Spraying in the first 40 days of the rice crop is not necessary. Farmers, when presented with this rule, which is in complete conflict with their normal beliefs, would get into cognitive dissonance. Their obvious response would be to reject this new rule and say that this is because it is not their normal belief. But to help the farmers resolve this dissonance, we would invite farmers to experiment by leaving half their fields that will not receive sprays in the first 40 days of the crop, and the other half using their normal practice. At the end of the season, we would compare the yields of the two crops. The slide shows the results of the farmer participatory experiment to help them resolve cognitive dissonance. You will notice that farmers reduced their sprays from 3 to 2 and then to 1. Farmers spraying in the early crop stages reduced from 68% to 20% and then to 11%. The most important change was their beliefs. The beliefs that leaf feeding insects can cause severe damage reduced from 77% to 28%, and that leaf feeding insects can cause yield loss reduced from 74% to 9%, and that leaf feeding insects had to be sprayed early reduced from 62% to 10%. Next, I would like to talk about the cognitive game that we developed to convince farmers about new ideas. Cognitive techniques are used in psychology to challenge and modify maladaptive thoughts, beliefs, and images. Rice farmers generally overestimate losses from pest attacks and thus make unnecessary insecticide sprays, a loss aversion behavior. The cognitive game to facilitate the computation of yield loss from whiteheads, a symptom of rice stem borer attack, was developed to help farmers make adjustments to their biases. After participating in the exercise, farmers reduced their insecticide sprays for stem borers control by 22% and their intended insecticide expenditure the next year by 45%. The control farmers, on the other hand, did not reduce their spreads. Farmers who have done the game reduced their estimated loss from whiteheads by 27%, while those there were no reduction in the control farm. Farmers also reduced their controlled expenditure and perceptions of loss by 43 and 54% respectively. Compared to the controlled farmers, higher reductions in beliefs were also found in farmers exposed to this exercise. This slide shows the yellow stem borer. The adult is on the left, and the worm that attacks the stem in the middle, and the symptom it caused called whiteheads on the right-hand side. Because of plant compensation, we find that when rice plants are attacked by very low levels of whiteheads, there is in fact overcompensation, and generally a rice plant will need to be attacked by at least 5 stem borers, which is very rare in general. Plant compensation. Rice stem borers damage hills, have increased tillering, increased percentage of productive tillers, increased grain weights, increased photosynthetic rates, and assimilate translocated from stem borer injured tillers to the healthy ones. This chart shows the typical crop yield insect infestation relationships. You will notice that at early stages, where the damage is very low, is a phase we normally call overcompensation. And then compensation occurs at the higher damages, and only when injury is very high would you observe yield loss. In this participatory cognitive game, we invite farmers in groups of 5 to 10 to participate with discussions, and the facilitator uses a framework to obtain information from farmers and then convert them to loss and gains. And then the discussions about cost and management rationale. This is the framework we use in the cognitive exercise. First, we obtain information from farmers: number of whiteheads per meter square, loss if no control in kilograms, price of rice, loss in monetary terms, and the control costs they had spent in the last season. In the part 2, we convert the whitehead per meter square to per hectare, calculate the grains per panicle, and obtain number of grains lost in 1 hectare. With the weight of 100 grams, we compute the total weight loss from whiteheads and then loss in monetary terms. Here is a typical example of the data we obtained. Farmers reported 2 to 10 whiteheads per meter square. They perceived that would cost them 1,000 kilos loss, and the loss in terms of monetary terms will be 7,000 pesos. And the cost of control the farmer implemented last season was 1,500 pesos. In the second part, when we converted those figures provided by the farmer, here is how it looks like. The whitehead per meter square is converted to whitehead per hectare, and that's about 50,000. The grain per panicle is about 80 in the rice they were growing. Total grains lost was about 4 million. And since the weight of 1,000 grains is 2.5 grams, the total loss was just 100 kg. And the market value of 100 kg was 700. And you can see clearly that the farmers perceive that they will lose 7,000 kg and thus spend 1,500 pesos to control the pest. However, when calculated, we can see that the loss is only just 100 kg and loss in terms of monetary terms 700 pesos. Thus, the farmer completely overestimated the loss by at least 10-fold. We tested the cognitive game in a replicated trial where you have an experimental group of farmers that does the exercise or the game and a control group of farmers nearby that had not been exposed to the game. Changes in farmer management in terms of percentage reduction between those who have exposed and those who were to the game and those who control is shown in this chart. The number of sprays for stem borers was reduced by 22% in those who had performed the game. The expenditure for control by those who have performed the game was 57% reduction, whereas the control farmers were zero. Similarly, the estimated loss from whiteheads by farmers had no reduction in the control, but 27% reduction in the farmers who have performed the game. The next innovations that I'm discussing is about multimedia campaigns. The aim of the campaign was to motivate rice farmers in Vietnam to modify their beliefs and pest management practices together with seed and fertilizer inputs. This program was locally called Bagian Batang, or Tree Reduction, Tree Gains. The campaigns were using leaflets, posters, billboards, and radios when they were launched. Farmers' practices changed significantly in this after the campaign. For instance, farmers' insecticide sprays reduced by 13 to 33%, while their seed rates dropped by 10% and nitrogen rates by 7%. These practices were supported by modifications in beliefs and that favored high inputs. Farmers also changed their perception of loss. The campaign stimulated the Ministry of Agriculture and Rural Development in Vietnam to provide additional resources and funds to all provinces to reproduce the materials the campaign produced and the campaign process in all the provinces, and this eventually reached more than 3 million farmers in South and Central Vietnam. This slide shows the poster that has been used by the campaign, the leaflets, both sides of the leaflet that have been used by the campaign. And this is the billboard used, where this billboard was placed in strategic places along the roadside. We also invited about 1,000 farmers to participate in experiments, leaving their fields with the tree reduction program and the other half of their fields as control. And you can see in this table the significant reduction in insecticide sprays in the experimental plot, and reduction in nitrogen use in the experimental plot, and reduction in input costs in the experimental plot, and the resultant increase in profits in the experimental plot. This table shows the results from after the campaign, the difference between the pre and the post campaign. And as you can see, the seed rate has been reduced in post campaign. Nitrogen rate has been reduced in post campaign. Significant reduction was in insecticide use, reduced in the post-campaign. The yields, not much difference between those in pre and the post-campaign. Next, I would like to talk about an ecological TV series we use to motivate farmers to change their practices to observe ecological engineering practices. Developing this series of television series, we used the entertainment education process in the design and implementation. The purpose of entertainment education programs are to entertain and educate so as to increase the audience members' knowledge and create a favorable attitudes and shift the norms and change their behavior. An important component for farmers to understand is the role of parasites or parasitoids, which are very tiny insects attacking the pest eggs. As these insects are tiny, it is difficult for farmers to see the parasitoids and appreciate them. Since bees are bigger and easier to observe and also very well known among farmers, farmers were taught to observe the bee population as an indicator of parasitism. The parasitism concept is little known to rural farmers, so we had to create a new word for the parasitoids, and they were called farmers' name was small bees or parasitoids. So farmers are now acquired a new term called small bees. The small bee concept, parasitoid concept, was presented in 3 simple rules in a cluster. They are: flowers on the buds provide food to attract bees and small bees to my field. The bees and small bees will help me control the hoppers invading my fields, so I don't need to use insecticide. If I apply insecticide, it will kill the bees and small bees. These messages or simple rules were presented in a television series. This table shows the comparison between those who have viewed the TV series and those who have not viewed the TV series in the randomly collected interviews. You will find that for seed rate, the difference between the viewers and non-viewers was a reduction of about 12%, and that is significant. Nitrogen rates were reduced for about 6%, and the insecticide sprays were reduced by 24%, and the percentage of farmers who has stopped spraying completely was about 4%. The yields between those viewers and non-viewers was in fact an increase of about 3%. An important thing about the television series approach was what the farmers had learned from the television series. You'll find that farmers have learned that nectar flowers can attract natural enemies to help pest control. Nectar flowers can help reduce insecticide use. Nectar flowers can reduce production costs, help in reducing chemical inputs, and help in increased net income and increase natural enemies, and also reduce pest infestation. In conclusion, while it is important to develop ecological technology, it is also very important to communicate these technologies to farmers. In the end, farmers will be the implementers. It is thus important for researchers to learn the main constraints of farmers and develop means to help them appreciate ecology. I presented a few examples where such approaches have been successful. More emphasis will be needed to focus on communicating ecology so as to increase farmers' ecological literacy. I would like to take this opportunity to thank the organizers for inviting me to share these few ideas with you, and I hope that I also thank you for your listening, and I hope that these ideas will be helpful in your future. Thank you very much.